Islam. And I have already requested Professor Tariqul to complete his presentation within 25 minutes since we have elapsed some time. So Professor Dr. Mustafa Al-Mamun sir, please introduce him.
Can you hear me?
Fine, sir. Fine, sir.
My video is on, all right?
Yes, sir. You are visible, sir.
Okay, thank you. So welcome to all to this session system engineering, faculty of engineering and built environment, University Kebangsaan, Malaysia, UKM. And he is also a visiting professor of Kyushu Institute of Technology, Japan. So I would like to recite his biography in brief. Of course, Muhammad Tariqul Islam is a senior member of IEEE. He is currently professor of Department of Electrical, Electronic and Systems Engineering, UKM, and a visiting professor with the Kyushu Institute of Technology, Japan. He is the author of and also co-author of about 500 research journals articles, nearly 175 conference articles, and a few book chapters on various topics related to antennas, materials, and microwave imaging, with 22 inventory patents fields. Thus far, his publications have been cited 6,650 times, and his high index is 40. His Google Scholar citation is 9,500 and high index is 46. He was a recipient of more than 40 research grants from Malaysia government and also from Japan and Saudi Arabia. Telecommunication Award for his research and innovation and Best Researcher Awards at UKM in 2010 and 2011. He was a participant of 2018 and 2019 IEEE AP MTT EMC Malaysia chapter and Excellent Award. He also won the Best Innovation Award in 2011 and the Best Research Group in ICT niche by UKM in 2014. And he has many more other things to mention, but due to shortage of time, I'm avoiding those things. So finally, I would like to say that he is ranked among the top 2% world scientists in career, published by Stanford University in November 2020 in the field of telecommunication. So now I would like to request Professor Tariqul Islam to start his keynote speech on electromagnetic sensing in healthcare solutions with planar antenna. Thank you.
Okay. Assalamu alaikum and good afternoon from Malaysia.
Wa alaikum assalam. Very nice to see you here.
Yeah. Thank you very much, STI organizer and especially Professor Abdul Razak to invite me to deliver a talk on my research. Today, I would like to talk on electromagnetic sensing in healthcare solution with planar antenna. Okay.
Yes, it's visible to us already. You have shared.
Okay. Okay. Thank you very much for my bio. I'm from UKM, and this is Malaysian National University. We are a research university. Apart from teaching, we are one of the research universities in Malaysia among 5 universities. If you look that here, that we have the same number of postgraduate students, like bachelor students here, almost 1,000. And this is my microwave research laboratory with some activities and some of the chambers, some of the research facilities that we use for our research. Okay, I'll talk today about electromagnetic sensing through a planar antenna. As of we know that electromagnetic sensing is now widely used in breast imaging, like tumor detection, head imaging, stroke detection, security imaging, like this. You see salinity imaging, heart imaging, and humidity sensing, detection of strain evaluation, and glucose sensor for bloodless diabetics. All right. Uh, I will talk about breast imaging, tumor detection, which is very much in line with by following the IR4 capabilities, and the tumor can be detected using machine learning. If we usually post the data through cloud, so the medical practitioner can handle the patient remotely. More than 1.8 million new breast cancer cases diagnosed every year worldwide. So increasing population and longer lifespan contributes to rise of this cancer. Actually, it is not an incurable disease, but the key factor is reliably diagnosis in the early stage. Usually, the survival rate is more than 97%. Ultra-wideband antenna-based microwave imaging for breast cancer has the potential to be used in cancer detection. Usually, the ultra-wideband UWB has bandwidth more than 500 megahertz, and it is a very low power microwave, about 41 dBm, and it high transmission rate, and it is low cost. The frequency of operation is about 3.1 to 10.6 gigahertz. The beauty of using of microwave imaging is it is a non-ionizing radiation. Okay, and with that UWB features, we can go for high image resolution. Okay, and of course, it is non-invasive. Okay, no contactless. But the present technology for these types of tumor detection includes X-ray mammography, which is high number of false negative diagnosis, and of course they use the radiation ionization. Okay, requires uncomfortable compression. So these features reluctant for the patient to go to early diagnostic system. Some of the others are like X-ray tomography, which is of course involved with more radiation. Ultrasound system, there is few detect, but it is difficult to detect deep lying cancer tissues. But so far we trust on MRI, which is accurate method, but it is really high cost and time consuming. About 25 to 30 minutes it takes to detect through MRI. Presently available MRI machine is 3 Tesla, which is 127 megahertz. Okay, but mostly 1.5 Tesla. There is few research-based MRI machine is available in Germany. It is 7 Tesla, which is 300 megahertz. But if you see that when we use the microwave-based technology, it is UWB. It has a 500 megahertz, and it is equivalent to 11, almost 12 Tesla can produce. So it's really very high resolution picture image can be constructed if we use the UWB system, and accurate localization can be possible. Look at here how it works. This can be the prototype using the microwave technology, microwave based technology. I have also shown here some of my laboratory based prototype, which is ready for marketable product. How it works? It works like transmission of very low level of microwave energy. Then different dielectric properties such as dielectric constant, permittivity, and conductivity, it can refer back the signal. Usually, the cancerous cells are highly water content, more than 5 to 6 times. So, size and location of the tumor can be obtained from the backscatter signal. Okay, so how it works? It like automated microwave imaging, or you see that the tumor can be detected, like if one sensor can transmit and another sensor is received and can get the scattered signal to identify the unwanted tumor from if it exists. Okay, so it consists also with the rotation platform and with some processing element. Okay, this can be single transmitter and multiple receiver. We have also come up with one system of 9 antenna, the motor based antenna mounting here, and then we have to maintain a certain gaps between the sensors, about 2 centimeter around the base phantom. Okay, the antenna are connected with switching, so we can get the different signal with the backscatter parameter, which is connected to the power network analyzer. Okay, so actually the system accuracy, the image accuracy depend on the sensors. So we have also extended our sensor number, and by utilizing 16 sensors antenna element, we use multiple transmit and multiple receive. What we do here, one antenna transmit and second antenna receive, and third antenna transmit and fourth antenna. So odd number of antenna is transmitting the signal around the tumor, and even number of antenna is receiving the backscatter signal. With that, we can perfectly detect the backscatter signal. To implement these types of imaging system, we utilize a very high sensitive microwave based antenna, which is one of them is called planar antenna. So how we start? We come up with the spec, like for example, for this case, if it is microwave based imaging system for tumor detection, we try to identify like the frequency, gain, size, then we decided the topology that we use, and then we go for design computational method. After that, we fabricate and we characterize at the end. We have designed a variety of shapes of patch antenna, like rectangular, circular are the most common. If we see that we have few shapes here, we come up and we have presented and published in different reputed journal, including Transaction of Antenna Propagation Magazine, with you see that asymmetrical shape feeding method, which is very novel and can control the current of the system, and it produces a very high gain. We also developed some planar based antenna for small satellite, microsatellite, symmetrical shape, and for omnidirectional pattern. We do some design for small satellite, more like nano satellite, and which is implemented and which is now orbiting in the Earth through Japan universities. And we also design few sensor-based antenna for microwave-based system. One of them maybe we discussed today, which we utilize for tumor detection system. We have modified the Vivaldi-based Vivaldi shape antenna by to achieve the compactness, achieve the compact, and we have managed to receive about 88 millimeter of size. You can see in the picture. The height is 88 to 75 is width. It is a slotted Vivaldi antenna. Okay, and it is a patch type, planar type of antenna, which is very much suitable for imaging system. With our modified slotted Vivaldi shape, we achieve a very high performance efficiency, almost 92% with a 9.8 dBi. Okay, so nonetheless, to mention that if we have a high gain, it can penetrate with the tumor and with the human phantom and body. Okay, that's why the gain performance is very much crucial for these types of research. Okay, we also utilize some extra parasitic element to improve the more performance, to get more bandwidth, to achieve the high resolution performance. Okay, so we have done this by utilizing the parasitic element, and the fractional bandwidth we almost achieve 100%, more than 100%. And to reduce the electronic waste, which is now very important to consider, we also come up with some sensor design with thiophene based material, which is organic. Okay, so it is easily decomposed in the earth, a very environment friendly compound. With that, we maintain the environmental hazard and promote economical benefit. So and it, on top of that, it has also flexible performance. So we have a plan to implement it in a flexible bra to detect the tumor. Okay. Before going to develop the sensor, we have done the morphological analysis, and we can see some parameter. As my time is limited, I'm not going to the analysis that we have done here, like the structure. So it clearly we have to maintain these structural performance and the morphological performance in our order, so that it can work with the high permittivity characteristics. There is some performance measurement we have seen here. All right, and you see that some measurement performance by within the carb sensing, and it is really shows with the bending with the bending capability. It really shows a very good reflection coefficient. All right. If we really come up with a very compact design, we can incorporate the metamaterial structure, and we got a very successful outcome with the metamaterial, which we call actually the artificial medium with electromagnetic periodic structure. Okay, smaller than the wavelength. It has a negative permittivity and permeability. Okay, that by incorporating these metamaterial with our design, we able to reduce the size and stable the performance. Okay, we can see that one of the design here, that meander line shape, how we control the current with this shape to control the negative performance, negative permittivity values. Okay, to achieve the good efficiency and to reduce the size. All right. So normally to calculate that, we use the Nicholson-Rouse method. Okay, and you see that we come up with a different metamaterial type unit cell to improve the efficiency and the gain. Okay, as well as the compactness. All right, few designer here, and if you look the compared to our earlier design, which was almost 72, even we can able to get it dimension of 3.95 with 4.8 millimeter. Okay, by utilizing these types of metamaterial to improve the performance. Okay, and with that small size, we achieve a higher bandwidth, and we can combine multiple unit cell to achieve our desired performance. Okay. Okay, few more design on metamaterial load the antenna, which I show. Okay, you see that this is the metamaterial structure in antenna, which give us a very wide bandwidth of okay, of 9.2 dBi gain. All right, so we usually measure this prototype in near field Satimo to get the the accurate result okay, in different frequencies. All right, these are the output. I mean, these laboratory prototype for microimaging system. We have finally we come up with the 9-element system and 16-element Vivaldi antenna system. Okay. Okay. As I mentioned that the 16 element, we use multiple transmit and multiple receive, which give us a very good resolution. Okay, I will summarize the information. And you see by utilizing the optimization algorithm with different like delay and multiple sum and okay, we get the images of the tumor images clearly. Okay, and usually our target to from the 3 to 8 gigahertz because sometimes if we go more higher frequency, due to the body temperature, tumor characterization, tumor structure is slightly changed. So we have to consider that as well. Okay, so we so far develop few channels like 9 antenna array with 8 channel like 1 transmitter and 8 receiver, along with the 16 antenna array which 8 antenna with 8 receiver. Okay, now we identified 50-50 scanning position. Okay, as we know that for the safety reason we didn't yet go to the real measurement in the hospital, but it is under process. We are now under evaluation of ethical evaluation committee, but we have measured this research on by using the artificial phantom. So we have tested in different phantom, for example, like commercial phantom, which is usually made of skin layer, breast tissue layer, and tumor. The usually the skin layer is about dielectric constant about 38 conductivity of this amount. So what we tested, it is about 2.5 millimeter thickness of tumor. Okay, usually the breast tissue has a higher dielectric values, as I said. It is about 67. Okay, 67. So it can be easily we can detect from the backscatter signals as it contains high water compared to the other dielectric tissue. Okay, we also developed few phantom, homogeneous and heterogeneous phantom in our lab. We tested. Usually we use agar, water, and different sodium dihydroxide monohydrate. Okay, with different temperature, we come up with that with different tumor, different tumor, different size to detect. Okay, in imaging system. Okay, before we go to the test bed, we also have to test in different conductivity and permittivity, and we found that actually the permittivity increases with the frequency. Okay, conductivity increases with the frequency. All right. And we have start measured with initially from 2 antenna system around the human body. Okay, due to safety permission, as I said, that we go with that phantom. For laboratory test, artists look at the phantom to collect throughout the phantom to look at the position of the tumor first. Okay, and we detect in some tumor and 270 degree. Okay, for the our advanced system, we use different imaging algorithm like delay and sum, yeah, and coherence factor delay and sum, and iterative correction, correction ICD mass, which is iteratively corrected variation. Also, we do some variety like delay, multiple, and sum algorithm, and you see that our reconstructed image. Okay, our reconstructed image. So far, we have tested on 4 tumor. Okay, and we have also compared in terms of signal to mean ratio SMR values from backscatter signal. All right, so the results are compared between the conventional and our iteratively enhanced variant, and we found that really the iterative coupled mass has given a better resolution and better performance in terms of signal to mean ratio. Okay, so I can say that we have detected minimum tumor size of 2.5 millimeter by using 16 element antenna. Okay, total number of detected tumor is number 4, and it can deep inside 25 millimeter. Okay, it can be extended if we increase the antenna sensor, and we have planned to improve it to 32 antenna sensor, which we can go about 1 millimeter. Okay, these microimaging actually very promising in different healthcare, as I mentioned. Like we also are doing another project on stroke detection, which we call microwave head imaging. Uh, okay. We are detecting the blood clot in the brain through the imaging system. Few of our laboratory prototype that is now under investigating. Okay. All right. I think I'm on time. So in summary, what I can say, these types of microimaging system in compared to the existing other method, it is really unwanted compression can be done. And not considered the low power. Okay, much easier. It has not only the healthcare, these microimaging can be very have a good future to work on, like to detect the palm trees, some different input cases like worm can be detected using this, and also it has a good future work on oil and gas industry to detect the purity of the well. Okay. All right. Okay. These are, I would like to thank some of my collaborators, those who I'm actively working with them with this project. And these are the references I have used. And with that, I would like to thank and conclude my presentation.
Thank you very much, Professor Tariqul Islam, for your nice, comprehensive presentation. And I guess so many new things we came to learn. So now the floor is open for questions. Few questions may be taken from the audience.
Assalamu alaikum. Thank you, Professor Tariqul Islam. Actually, I have to know two aspects from your presentation. First of all, what about the health hazard of the electromagnetic sensing? And another thing is, what about the, false positive rate of, CT-based scanning and the electromagnetic sensing in case of the brain, imaging?
All right. So if you talk about the microwave imaging system health hazard, right? Uh, it is well known that as microwave imaging is using a UWB system, and it has a very low power, almost minus 40 dBm, which is zero point 0.00 milliwatt. So in terms of safety, it is safe. Okay, it is safe. And even nowadays, even mobile tower also give these types of advertise of in terms of the safety, safety things like, okay, I show you. Okay, even you see that in India, even they show that it is non-ionizing and very low radiation. Okay, this is first question. I think it is safe. And the second, you want to know about CT scan false.
False positive rate, for example, that's for the CT scan or MRI and
Yes.
the microwave sensing. That's just the comparative studies.
Okay. If you say because there is a less chance of false negative, because of like it can produce a very high resolution of image. Okay, with low diameter. So there is a less chance, and it can penetrate based on the sensor performance. It can penetrate quite high and deep. Okay, on that case, it has a good performance of in terms of false values.
So in your country, actually, most of the doctor, they are still preferring the CT or MRI based. So why not they are using, for example, this electromagnetic
Okay,
sensing?
okay.
Is it still in the, I mean, research
Yes,
level, or it has
it is.
some practical implication?
It is still in the research level, not yet come in the market. Maybe that's why. And you know that our medical practitioner is very much reluctant to take the more, I mean, the advanced technology. Maybe they are used to use the existing method. But I shall not give them the blame because it is not yet available in the market. So different university and different company also actively working on this, okay, to come in very quickly in the market.
And my last actually question is, I'm sorry, I'm asking a lot of question. And last thing is, for example, in our country, you see, doctors are not, I mean, scanning this sort of brain or the breast. Okay, they are dependent on some other, I mean, radiologist. So sometimes there might be some misinterpretation of the imaging, right?
Uh, yes, yes, because they depend on the report, right? Yes, yes.
Yes, exactly. This is.
Yeah, yeah, yeah. So if
So what about in Malaysia? The doctor, they themselves do it.
they do immediate scanning, they do immediate scanning. They no
The
need to.
doctor themselves, right?
Yeah, yeah. Even if you go to the doctor's clinic, they do immediate scanning, like like measuring of blood pressure and heartbeat rate, something like that. For CT scan, not for, I mean that for micro imaging like mammography and other things. But like for MRI, they cannot do that because, as I said, that MRI is still, it is time consuming, almost 25. I think those who already gone through that system, so our target is to make it like clinical environment, like it can detect, I mean that it can take the data by 4 to 5 minutes. Okay. So and it will be low cost compared to MRI. MRI is a huge cost involved, so it can be easily implemented in the clinic, types of very small clinic.
Okay, thank you so much.
May I now request reporters to display the certificates? Uh, Mustafa Mamun sir, can you hear me? Sir, your microphone is found muted.
Okay, okay, I can hear you. My mic unmuted now.
Okay, so it was a very scholarly discussion, and I think even though Professor Tariqul Islam found some difficulty at the beginning for joining, but at last we could be able to listen to his valuable talk. And thank you very much, all the audience, the participants, the session chair, and the speaker for assembling here, but to render a very good quality discussion. May I now request a reporter to show the certificate of contribution. So may I now request, yes, previous one, please. Yes, thank you. So STI 2020 organizing committee is immensely happy to confer certificate of contribution to Professor Dr. M. Tariqul Islam for his keynote space on a very timely topic. Thank you very much, Professor Tariqul Islam, for your valuable time spending with us.
Thank you very much, STI and you as well, for inviting me to share my research.
Thank you very much. Well, We are also delighted to have amongst us Professor Dr. S.M. Mustafa Al Mamun from University of Dhaka for sharing this keynote session. It's a certificate of appreciation proudly presented to Professor Dr. S.M. Mustafa Al Mamun, sir.
Okay, I gladly accept your uh, honor.
Thank you very
And
much, sir. Thank you very much, sir. Thank you very much, sir. Our team will soon send you e-certificates, and it's a great honor to have you. See you in the next time, inshallah. We'll soon start our next keynote session. So please stay with us. May I now request our reporter to display the next keynote session